All right, here is our final video wrapping up this little slide deck explanation of exponential models. So we left off right here. We talked about the difference between a growth or decay factor and a growth or decay rate. Our equation is still y equals a times b to the x, as we talked about back here a few slides ago, where a is the initial amount we start with, b is whatever we're multiplying it by every time. Mathematically, that's all that's happening. But you would rarely see the B, the growth or decay factor, actually expressed in words. People would not say that. I've never driven by a bank and seen a sign that says, our certificated deposits earn 103% of what they were worth the year before. No, they say they earn 3% per year. To take a more relevant example, we don't hear things like, every day there are 110% more coronavirus cases than there were the day before. What we hear is something like the cases are growing 10% per day or 20% per day, or they're doubling every 3 days. Those are the sorts of things we hear. Those do not quite fit with the math in the equation. So the translation between the daily or weekly or monthly rate of growth or decay, if it's something like the amount of value your car loses every year, and the daily or weekly or monthly growth factor, which is the number you actually have to multiply by, is this incredibly simple equation: B, the factor, equals 1 plus the rate. Keep in mind that the rate is going to be usually some fraction or decimal, like 0.05 if it's 5%, or it might be negative if it's a decay, like negative 0.1 if it's 10%. So it's really like 100% plus or minus a few percentage points of growth or decay. That's typically what these examples tend to look like. All right, so let's do some examples. Take a look at these two. The initial value, the A, is looking at you. And then there's a number in there that is either the growth or decay rate or the growth or decay factor. You've got to figure out which of those two things it is, and whether it's a rate or a factor, and whether it's growth or decay. Pause the video, take a second, write down your best guess for each of these two equations, unpause it when you're ready, we'll fill it in. I'm going to hold really still so you can't tell if you've unpaused it or not, just to mess with you. Ready? I bet that was awkward. I bet that when you weren't sure if you had unpaused or not. Yeah. Let me tell you something. My jokes are a lot harder to tell when nobody laughs, but that actually is about the same as I do it in class. All right. So this first one, that $20,000, that's going to be my initial value of the car. It's losing 20% in value per year. This car is plummeting in value. It is losing value very, very, very quickly. If it's losing 20% of value, that is a rate. So my B, the number that I actually put in the equation, is going to be 1 plus my rate. My rate is 20%, but it's losing value. So it's negative 20%, or 0.2. Well, what's 1 minus 0.2? How about 0.8? And that's my decay factor. Each year, this car is worth 80% of what it was worth the year before. Raise that to the power of however many years we're talking about here. A $20,000 savings bond gains 3% in value each year. So again, that $20,000 is my starting point, my initial state. If it gains 3% in value each year, that is, again, a rate. So it's going to be 1 plus 3%, which is 0.03. Well, 1 plus 0.03 is simply 1.03. And we'll raise that to the power of X, or the number of years that we hold this bond. Each year it's worth 103% of what it was worth the year before. Again, pause the video, answer these two questions best you can, figure out, are you being given a rate or a factor, and are we talking growth or decay, and write the equation. Pause it. All right, I'm going to assume that you've unpaused it by now. We're back to it. All right, our colony of feral cats. We have 30 feral cats. That's our initial state. Doubling every year. That means I'm multiplying it by 2. That is the factor. That's not the rate. This is one of the situations where you actually will get the factor in words. If we're talking about doubling or tripling, that's just times 2 to the power of the number of years. Interesting side question there. What's the rate? Well, 2 is 1 plus what? 1. So 1 is 100%. This is 100% growth rate. Something that is doubling every year is growing at a rate of 100%, or whatever its previous value was. Something tripling every year is growing at a rate of 200%. If something is growing at a rate of 900%, that means every year it's actually multiplying by 10. Fun side note. Let's just leave that as a 2. Here we got our 5,000 people in the World Series of Poker times. Now, it doesn't say 10% get kicked out every day. It says each day only 10% are left. Day 1, 5,000. Day 2, 500. Day 3, 50. Day 4, 5. Each day we only have 10% left from the previous day. So that is actually the number we're multiplying by. We're multiplying by 10%, or 0.1. In other words, we are losing 90%. We have a 90% decay rate, which gives us a 10% decay factor, but that was what they actually gave us. They gave us the factor in this equation, not the rate. Raise that to the power of x. So these are 2 examples where the factor is a thing you're actually being given, as opposed to where we usually get the rate. Last couple examples here. Let's do it backwards. Let's take the equation and figure out from that what's the rate, what's the y-intercept, and then let's talk about them in plain English for a second. So take a minute, look at these 2 equations, our example 1, our example 2, write down or make a mental note, what do you think the initial state is, and what does it mean in the context of this question? What is the growth or decay rate, and what does it mean in the context of this question? I'm not going to type these answers, I'm just going to say them, so listen closely after you've unpaused the video. Pause it, write your answers down, unpause when you're ready. All right. So this is my 1 plus r. There's the 1. That's got to be the r, 0.023 or 2.3%. This is a number that's bigger than 1, so this treasury bond is growing at a rate of 2.3%, which is about right for a treasury bond. Every year it's worth 2.3% more than it was worth the year before. The 500, that's what we start with. That's how much I paid for the bond. I bought a $500 treasury bond. It's now growing at a rate of 2.3%. That's my interpretation of this one. I bought a $500 treasury bond. It is growing at a rate of 2.3%. Temperature of the can of soda in a bucket of ice water measured in degrees Celsius. Well, again, this 0.62 is 1 plus or minus something. That is going to be 1 minus 0.38. 1 minus 0.38, so negative 0.38, it's negative, so its decay is my decay rate. So I'd say this can of soda is cooling 38% per, what do we have here, minute. Every minute it cools 38%, which if you think about it should kind of make sense. 0 degrees Celsius is the freezing temperature of water. So it starts up here at 28 degrees, which is warm room temperature, and it keeps getting closer and closer, but by a percentage, not by a constant amount. So that last degree takes a lot longer to cool than that first degree. That first degree, it's got a really big difference between the ice water around it. That last degree, that difference is not much, and it's not cooling much anymore. So we get a nice curve as it comes in and cools down. I said it as part of that, but that 28, that's our initial value. That's our temperature, 28 degrees Celsius when we start. So I would say the can of soda was 28 degrees Celsius when we put it into the ice water, and every minute it cools 38% of its previous degrees, approaching 0. Hope that was helpful. You are now ready to take a stab at your assignment, which I can't tab over to from this recording, but you have assignment 11, also posted in this worksheet. All the questions on assignment 11 should look exactly like the stuff we've done from this slideshow here.